Oh, hello everyone. Today we will start a new topic and the first topic, first unit, that is automata theory. And basically in the theory of computation, the first unit is related to the automata theory. So in the basically automata is nothing but the mathematical model using which we can accept the languages. So the point is, how can you represent the automata, or you can say the mathematical model. So for representing the mathematical model or automata, we draw the state diagram. So state transition diagram for the finite state machines. So this is nothing but the graphical representation of the machines, and it will show the behavior of the mathematical model, or you can say the automata. So for this state transitions diagram, basically uh, two important diagrams. In the diagram, there are two important components. So first one is the states. So for the states, we will represent the circle. Through the circle, you can represent the state, and through the arrow, you can mention the transition. So it means in the machines or mathematical model will show the state transitions diagram using the states and the arrow, and the arrow is nothing but the transitions. So when the particular machine will stay at particular states, it will take some inputs. By taking some input, it will reach to some another state. So right. So using this, it will show the transitions. So in the state transitions diagram, the state will be represented using the circle, and the transition will be represented using the arrow. Right. So this is the state transitions diagram, and using the state transitions diagram, you can show the automata. So in the compiler designing and the parsing, we are using the concept of the automata. So before starting the automata, we will find out the finite automata. So the first type of mathematical model or automata is finite automata. So why we are using the terms finite? Because finite number of states are there, right? So finite number of states are there. That's why we are using the terms finite automata. So if we will talk about the classification of the finite automata, so we can classify it into two different categories. First is the without output, and the second one is the with output. So in the without output, again you can classify in the deterministic finite automata and the non-deterministic finite automata. And with output, there are two different machines. That these are the Murray machines and the Mealy machines. So basically, we have four different type of finite automata. Two automata are related to the without output. So these two machines or mathematical model will not give the output, but they are using for accepting the language. So for they are using the regular language, right? So finite automata, those will not give any output. They are using for accepting the language, and the finite automata, those will give the output. They are basically using for the generating the string or language. So these for this we have Moodle machines and the Mealy machines. So first we will talk about the deterministic finite automata. So for defining finite automata, we have five different tuples. Using these five different tuples, you can give the definition of the deterministic finite automata. So we are using the terms deterministic, so it means we can determine what will be the next state, right? So it means even the machines will perform at particular state, it will reach to the next state by taking input symbol, but we can determine what will be the next state, because for every input symbol, it will reach to the one particular state only. It cannot reach to the multiple states, or it cannot reach to the number of states. Okay, so only there is only one transitions, but so by taking one input symbol, it can reach to the only one state. So for how can you define the DFA or deterministic finite automata? So we have five different tuples. Using these five different tuples, we can define mathematically the DFA. So what are these tuples? Q. So capital Q is the set, and in this set we can represent the number of states. Summation is the input string, so we are taking about the input symbols. Input symbols using the summations. Delta will be the transition functions, and Q naught will be the initial state. F will be the final state. If you are reaching to the final state from starting with the Q naught, it means you are accepting the language. You are accepting the string. right? So Q naught will be the initial state. So what is the major part of this definition? So delta will be the transition functions. So how can you define the deterministic finite automata? So through the transition functions, we can represent the deterministic finite automata. So in the transition functions, so we are representing that Q. If you are staying at a particular state Q, when you are reading one input symbol summation using from these summations, you are reaching to the one particular state only. So Q will take input symbol, it will reach to the one state, right? So this is the transition function for the deterministic finite automata. And F is the final state when you are reaching. So final state is nothing but the accepting state. You will start from the initial state, and when you are reaching to the final state, it means you are accepting some language. So this is these are the five different tuples for representing the deterministic finite automata. So now for defining the non-deterministic finite automata, again same different tuples are there, same different five tuples are there for defining the non-deterministic finite automata, right? So the major difference will occur when we are talking about the transition function. So in the same, the Q will be the capital Q will be the number of finite states, summation will be the input symbols, delta will be the transition functions, and the differences between DFA and DFA will we can represent using the transition functions only. Q naught will be the initial state, and F will be the final state for or accepting state. So for defining the non-deterministic, so it means you cannot determine what will be the next state when the particular state will take input symbol. So it means it can reach to the multiple state. So how many state it can reach? So how can you define the transition functions? Q will read one input symbol, it will reach to the 2 raised to the power q. So 2 raised to the power q is nothing but the power set of the state. So it means it can reach to the multiple states. So and how many combinations will be there? It will be the power set of the state. If two states are there, so it can reach to the four different states or four different states it can reach. Right? So these are the power set subsets of the Q. So it means we cannot determine what will be the next state. So this is the fundamental difference between the DFA and the NDFA. But these two are the finite automata. Those are related to the accepting the language. And for accepting the language, we have the final state. Right. So in this example, finite automata is given to you. Number of states, how many number of states are there? Four number of states are there. We can give the name of this state A, B, C, D. So these are the set of states. So that's why we are giving the name of this as a finite automata. But we need to consider that this is the example of the DFA or NDFA. So if the A is the initial state, because using the arrow, we are representing that A is the initial state. So A will take input symbol 1, it will reach to the C. But A will take input symbol 1, we are representing one cell 2, so it means it will reach to the itself. So it means by taking input symbol 1, it can reach to the C as well as A. In the same manner, A can reach to the state B by taking input symbol 0, and A can reach to the itself using the cell loop by taking input symbol 0. So it means this is the example of the non-deterministic finite automata. So we cannot determine because input symbols are 2, 0 and 1. For each input symbol, they are reaching to the more than one state. So we cannot determine what will be the next state by taking input symbol. So this is the example of the non-deterministic finite automata. And because and D will be the final state, and we can represent the final state using the double circle. So we can ask to you that which language this particular finite automata will accept. So the initial state is A. We will start from A and we will reach to the D. So we will start A. We will accept the language when we are reaching to the final state, and that is the D. So from the double zero, if the double zero will be there or double zero will be the substring of a string, it will be accepted by these machines, or double one using the second path from the C. Double one will be there. Then using this double one, if the double one will be the part of the substring, your machines will accept this particular state. So it means using this diagram, we can define that if double zero will be there or double one will be there in this string or in this thing, then this machine will accept these type of strings. So this is the example of the non-deterministic finite network. Okay. So in the next class we will discuss about the rest of the part of the deterministic finite network. Thank you.